A data structure is an object that holds data. In particular, its entire job is to store data and to provide an interface for adding, removing, and accessing that data. In past programming courses, you may have written classes to represent an object, like a book. The book might have some variables like its title, ISBN, year published, and some methods that help us interface with that book. However, this is not a data structure. The book class would allow us to create a variable for one book at a time. If we wrote another class to store a list of books, then that would be a data structure. Notice with this example Smart Book Array, it contains an array of books inside of it, and it has methods that act as an interface to add, remove, and find books that it is storing. A data structure will store a series of some kind of data, such as an array, though we will learn about other ways to store data in this class. To the eventual user, usually another programmer, they don't care how the data is managed, they just care that they can add, remove, and access the data. Ideally, when writing a data structure, it should be generic, so that you could store any data type in it, reusable, so that the data structure could be used in many different programs, robust, offering exception handling to prevent the program using the structure from crashing if something goes wrong, and encapsulated, so it handles all of the inner workings of dealing with the data without the user having to write special code to perform certain operations. When I'm thinking of writing a data structure, I think of it as if I'm going to create and sell a library of data structures that other developers at other companies can use in their programs. If I'm selling my data structures package to other businesses, my code should be dependable, stable, efficient, and relatively easy to use. Algorithm analysis is the process of figuring out how efficient a function is and how it scales over time, given more and more data to operate on. This is another important part of working with data structures, as different structures will offer different trade-offs. So for example, maybe structure A is fast at inserting data, but slow at finding data, and structure B is slow to insert data, but fast to find data. Which you should use depends on what you are implementing. As an example, let's say we have a sorting algorithm that, for every n records, it takes n squared time units to find an object. So for small amounts of data, this might be fine, but as we get a lot of data, things slow down very quickly. Note that we're thinking in general terms of time units, because different computers will run at different speeds. We're not concerned with the exact amount of time, but the general time growth. Data structures are a common thing to learn about in computer science and software development because most software needs to store and manage data. Many structures have already been written and are out there for you to use, so you don't necessarily need to know how to implement a given structure. So for example, C++ has the STL vector, list, map, and more. But part of making informed design decisions about what structures to use, where, requires some knowledge of how these structures work. So while you may not be writing your own linked list every time you need one, it is easier to learn more about how these things work by writing your own. So when studying data structures, we look at how structures work, their efficiency, and we actually spend time coding them so we get more familiar with how they work than just reading about it. Throughout this course, we will be stepping through and coding data structures like a smart dynamic array, linked list, stack, queue, binary search tree, and hash tables. Working with all these structures will also help you understand other structures that are out there. And we will also cover some software development practices along the way too.